So if W is expressed in barrel per day, it has to multiply by 24 and 60 to be barrel per minute, right? Or to divide it by, because the amount of barrel per 1 day is a lot. But if we have just 1 minute, it's a fraction of that much, right? So we divided by 24 and divided by 60. 24 multiplied by 60 is 1440. Believe me, I use a calculator and do that. It's 1440. Put it there, do the rearrange it, and we get retention time, the relationship between retention time from this table, okay, equal to 1440 multiplied by volume from another table, okay, divided by W, which is a volumetric flow rate that the separator can handle. Just that, just this equation, okay, very good. Okay, I show you that there's a d squared multiplied by L, d multiplied by L, d squared equation thing. That one is a good equation, okay, don't get me wrong. But there's a more accurate way to get the gas capacity of the separator. The more accurate way is to use the manufacturer field test data. They test it already and they sell it. So we don't have to worry about the slenderness ratio because they make it so that it is in the recommended range. Okay. So the actual separator has more internal components and is different from the calculation. Calculation may not account for all internal components, right? But if you do the test, it accounts for all internal components. Okay. So why do we learn about a theoretical way to get the gas capacity than if we just use a chart? You get curious about this? Why do we care about any of this? See? Why do we care? Anyone want? Can I get it back? The sheet? Why do we care about the calculation? What's your name, man? Olivia. Why do we care about the calculation part if we just use the chart? Supposed to answer no, that is correct. Check board or something. Most of the time when I do it, I don't actually check what it's just a chart and it's done. But I want you to know about that anyway, to learn the basic principle behind the chart. Okay? What is the basic principle behind the chart? Why should it be the way it is? Look at the formula, you will see that the size of the vertical separator for the gas capacity thing, okay, where is it? Is dependent upon Z, right? And that Z is dependent upon the molecular weight of gas. Molecular weight of gas depends on the specific gravity, correct? So specific gravity of 0.55 methane or 0.6, 0.7, 0.8. So when the specific gravity change, Z change a little bit, not very much, okay? But it changed. So the size of the separator depends on temperature. What temperature that we are doing? It depends on pressure. What pressure that we are doing? Okay. So if separator work for one pressure and we double the pressure, will it still work? Or we decrease the pressure by double, will it still work? Maybe, maybe not. So I want you to know that the size of the separator depends on pressure too. Okay. So that is why when you look at the table, for example, the first graph, gas capacity mmSCF per day. Okay, this is the gas capacity of vertical low pressure separator. When it says low pressure, we have operating pressure of 10, 20, 30, 40, 60, 80, 100. So because what we do is depend upon pressure, right? So the size that we need depend on pressure. That's why pressure component is here in the chart. So you don't need to get too worried. Why do we have to worry about the pressure? why the selection is dependent upon pressure. Because it is in the equation, so that's why it's popped up here. So what you do is, let's say you know that you will operate your separator at 60 psig. So you start from 60 psig, and you try, okay, if we have 36 inch by 10 feet, how much gas that it can handle? You draw the arrow until, this is kind of trivial, right? You know how to do it, right? Okay, read the line and read the value, and you get 6 mmSCFD. Done. The difficult part, it should not be difficult. You should select the right chart. If this say vertical, you use vertical. If it's horizontal, use horizontal. I don't expect you to select the wrong chart, okay? But I have to check whether you can use the chart anyway. So I don't want you to fail because you did print it. Okay, so that's why we print it for you. But I want you to know that there's some basic principle behind the chart. It's not just pop up. They do the test, yes, but the chart work at a certain pressure. Okay, at one pressure you may need one side of separator. At the lower pressure, the same size of the separator can handle less gas capacity. Makes sense? Because it expands. Okay, because gas expands. And so, and you want to know what kind of information that should be required for the chart, or what is the assumption that the chart made. We have equation depend on compressibility factor, right? And compressibility factor depend on the fluid composition. This one doesn't tell anything, it just says gas. So they say, okay, natural gas on average maybe 0.6 or 0.7. So if you use something else that is different than this chart may not be applicable. However, it is a good start, okay? Even though it's not directly work. Because at the end, your company will ask you to add some safety factor anyway, maybe a little bit. Okay. Do I print those charts for the exam? No, it will be provided. Do I print the table for the open book exam? If we have open book exam ever or any, okay? No, it will be provided if we have open book exam. Okay. This chart is for high pressure separator, low pressure separator. So when the pressure gets lower, gas expands and the same size of the separator can handle less gas. Okay, same thing. So this is vertical high pressure. Just read the chart, start from the pressure, go up, and then read the gas capacity. So this is a vertical one. Okay, for horizontal one, there's a little bit trick here. You see the dashed line, go up, reach the line on the most right, and then go up, turn right, go up, turn right again. So this telling you, it is depend on whether it's half full. The first line on the right hand side is the half full. The second one, or the middle one, is the 1/3 full. The left one is 1/4 full, 25%. So if we have the pressure of about 85, and we use the separator of the size 30 inches by 10 feet, so we go up until it reaches this point, then turn right. So if we do half full, we don't need to do anything, we just go straight. Okay. If we do 1/3 full, we go up a little bit to reach that line and then turn left. If we do 1/4 full, we go up more, up and turn left and turn right. So this means this is a gas capacity, right? If we have less and less and less liquid, it handles more gas. Oh, names look the same. Okay, Joe Miller. Hi Joe. Why when we have less liquid, we have more gas capacity?
Because less space is filled with liquid.
So more space is for gas and the velocity gets slower, right? This is consistent with the derivation that we do, right? So now you kind of understand the theory behind it, right? It's just about the velocity, the volumetric flow rate divided by area. So liquid level go down, more area means it flow a little bit slower. So that's why For horizontal, you have to vary whether it's half full, 1/3 full, or 25% full. So this one is high pressure. It's the same thing, but I tilt it so that it can be bigger on the chart. Horizontal high pressure separator. This one is gas capacity. This gas capacity of horizontal high pressure. Okay, different range of the size. Okay, different range of the size. And we have liquid capacity. So this time you have to use this part. This part I cannot really read it, so I type it here. So if you have retention time of 1 minute, use 1, 2 minutes, use 0.5, 3 minutes, use 0.33 or something. And how do we know how many minutes for retention time? We use another table which is given anyway, okay? Based on API gravity. Still remember that? Okay. So this line is 25% full, 1/3 full is the middle one, and the first line that we see is half full. Okay. So for liquid, it's kind of the opposite way. If we have it half full, it gets more liquid capacity. When we decrease the level, then the capacity for liquid go down because the space, the cross-section area get lower and it's kind of flow faster for the same given flow rate. Just do the chart. Question for using the chart. Question. No question, right? You can use the chart, of course. The chart is given independent of gamma or S or specific gravity. But the equation says it's depend on the specific gravity because this depend on specific gravity, right? So this means the chart already made the assumption on the typical natural gas that the factor won't change much. And if you look at the table, okay, the table will say, okay, settling volume for vertical low pressure separator 125 psi working pressure. 125 is working pressure. So they give you the size at a certain working pressure. Okay. For the different working pressure, you have another table. Okay, look at this table. Specification of standard vertical low pressure separator. What you have is model number, size, working pressure, inlet outlet gas connection, oil outlet connection. So you use 2-inch with thread. Okay. Standard valve, 2-inch something. Shipping weight, how heavy it is when it shipped. Okay, so this gives you the information. In the exam, you have to be able to select one size of this. For your senior design, do they need to use this? Yes, you will need to use this kind of chart to say, okay, I think I should use V6020 something. Okay. This table 1b gives you the settling volume for working pressure of 125 psi. Okay, so settling volume is V, and you remember W equal to 1440 V divided by T, right? Just use volume from this table. So if you do gas oil separation, just left column. Right column use this one, but normally for gas, oil, water, you have to split between water capacity and oil capacity somehow. We will talk about that later. For this lecture, we just gas and oil, gas and liquid. Okay, this is a similar chart for different working pressure. It tells you the size. Okay, different size, and this size, if you check, the slenderness ratio will be about 3 to 4. Okay, not more than 5, because they designed it correctly already. Settling volume as a V in that equation is here. Horizontal low pressure separator, H dash something is horizontal, right? So settling volume for half full, 1/3 full, 1/4 full is given. So is it difficult? Let's do something else that is a little bit more challenging. Okay, this is a chart. Go over it, right? Okay. Okay. You have seen the chart version. What about without the chart? What do we do? Without the chart, Arnold Stewart give you one example. Okay, we have one flow rate at 10 million standard cubic foot per day, a specific gravity of 0.6, 2,000 barrel of oil per day at API gravity of 40 degree, operating pressure of 1,000, operating temperature of 60, droplet size 140, gas viscosity 0.013. Actually, you read the book, that 0.013, they have to do some calculation to get that number, okay? Open another chart to get gas viscosity, and retention time of 3 minutes is recommended for this case. And we want to size a vertical separator. Okay, look at the difference. If we want the 10 mmSCF per day, and you know the pressure, you just go to the chart and get the size, right? Very quick, right? Look at this one. Step 1, get the turbulent flow drag coefficient. So get the density of liquid, get the density of gas, read the compressibility factor chart, put it in the formula to get V value. After get V value, recalculate. Oh, okay. See, rho G equal to 2.70 gamma P over TZ. This formula, where does that come from? It's from PV equal to nRT. We will use that later in the compressor part. Okay, the derivation is here. You will start from PV equal to Z nRT. N is mass divided by molecular weight. And molecular weight is gamma multiplied by molecular weight of air. Gas constant is 10.73 something. Okay, so density in the unit of power per cubic foot will be 2.6995 or 2.70, that formula. So basically this comes from PV equal to nRT. Okay, test this later, okay? Not on Tuesday. So once you get V sub T, put that back, calculate Reynolds number again. From Reynolds number, calculate new value of C sub D. So initially, we assume the value of C sub D equal to 0.34, right? Put 0.34 in the terminal velocity equation, get Reynolds number. From Reynolds number, get the new C sub D. After get that C sub D, get V terminal velocity again, calculate Reynolds number again, get new C sub D. Repeat this process until your answer doesn't change. Get C sub D of 0.851, then stop the iteration. Okay, that is turbulent flow C sub D. So why do we use a chart? Now you can see, right? The chart already includes the effect of turbulent flow of the droplet in there, and you don't need to iterate to get the accurate C sub D. Just use the chart, it's already included. If you don't use the chart, you have to iterate like this. Once get C sub D, put it there inside, then calculate diameter, okay? And liquid capacity, use that 3-minute thing, then you can get the height. Then calculate, compute the combination of diameter and height for various retention time, T sub R. Then, so basically, you have several diameter that you come up with, where the manufacturer may not sell it, or I think they will sell it, and those height, various height that you think the liquid level should operate on, do the calculation and find out if your retention time will match to the recommended value or not, and then you select the one that match. See, there's a height, the liquid height, and retention time, right? So they have to do more calculation, do the calculation for more cases and find out what case is good and then select that case. In the homework or exam to use this. So I show you both ways so you do know that. The chart is not just something that it looks easy but it's accurate, okay? You have to trust that chart. This way of calculation, it is more complicated and it doesn't account for every component that we put in the separator. That's the problem, where the chart comes from the test. So it's correct, but the number that not from the chart is, I would say it should be in the same order of magnitude. Okay, if we get liquid capacity of gas capacity of 5 million standard cubic foot per day, so another way of doing it should get somewhere close to 5, maybe 6, 7, 8, or 4 something, but should not be 50, 60. Okay, I'm not done yet. So you're good with the separation, right? Vertical separator, horizontal separator, use the chart, read the chart. And on Tuesday, you can show me the derivation of that Reynolds number formula and V equal to 0.011 something for terminal velocity. Can you? Yeah, probably. Okay, very likely. Let's take a look at liquid separation. Okay. We have emulsion when we have crude oil. Crude oil seems to have emulsion. Okay, it's easy to have emulsion with crude oil. And if we have paraffin, wax crystal will precipitate and it will stay at the interface between oil and water and it causes emulsion. So in the field trip, you already see oil in water emulsion, water in oil emulsion, or oil in water in oil emulsion or something. The complex emulsion, you see that, right? Okay. So let us skip this part. So when I say O/W emulsion is oil in water, and water is the continuous phase. So when I say W/O is water in oil, and oil is the continuous phase. So that's what you want to know. The problem with the emulsion is they cover it in the field trip a little bit, but what I want you to look at is not the definition, of course. The definition you can read it, right? It's two mutually immiscible liquid and it has sufficient agitation, then it creates a stable droplet of water in oil, a stable droplet of oil in water, and it doesn't get separate from each other easily. Okay. Agitation can come from valve, choke, or pump. Okay, when we have flow across the choke, it can have some agitation, right? Some mixing. So whenever you mix, it can form emulsion. So the solution from the field trip, James, Riley.
Here.
If you have emulsion, what do you recommend? What equipment do you recommend based on the field trip? Oh, okay, heater treater. Yes, heater treater. So field trip is useful, right? Okay. So if we have emulsion, we use heater treater. Heat it up and it will separate easier. So emulsion needs some kind of emulsifying agent. It can be some kind of surfactant or it can be drilling fluid, organic waste or resin. Okay, and it can be very small sand, fine sand, paraffin, wax crystal. Okay, so it can be clear particle sand or something. Basically, most of the time, how do you know that you have emulsion? Does it tell you? You do the test, right? Do the test, that kind of test. You have to check it. Okay, bottle test. We'll talk about that. Okay, let's take a look at the problem with emulsion. The real problem is the viscosity. Let's say my oil viscosity is 10 centipoise. Water viscosity is 1 centipoise. When I mix oil and water together, I form emulsion. Let's say I form emulsion. So, Salim, as
Right here.
do you think emulsion viscosity will be between 1 and 10? Oil is 10, water is 1, form emulsion with viscosity between more than 10. Can it be? Probably, maybe, or it cannot be more than 10 based on this graph. Oh, okay, let me check my question. Okay, that point maybe 10 centipoise for oil. And when I add more water, okay, 100% water, the viscosity is 1 centipoise. Without water, the viscosity is 10 centipoise. So when I mix them together and I form emulsion, suddenly do you think the viscosity can be more than 10?
Yes.
Yes, right? It can be a lot more than 10. Not just more than 10, it's not just 20, 40, it can be 250, okay, depending on how much we add. It can be a lot. So on the left side, if we have a lot of oil, we have a little bit of water, we have water in oil emulsion. On the right side, we have oil in water emulsion. So if we have almost 100% water, just a little bit of oil, put oil in, doesn't change viscosity much. It increases a little bit, okay? You see that point? We call it inversion point. Inversion from oil, so if we add more water, early on we have water in oil, right? When we add more water, we can have oil in water, okay? It inverse. One thing that you may want to know is when we go from the left side, we get one inversion point. When we go from the right side, we probably get another inversion point. It doesn't need to be the same. Okay. If you start with 100% oil, add more water, stir it, try to form emulsion. Okay. Add more water, at a certain water fraction, it inverts, right? So that's one inversion point. If you start from another side, 100% water, add more oil in, you can get another inversion point. What I found when I did the test is, when I have oil, add more water in, stir it, try to form emulsion, I get something like chocolate. It just brown thing, look like chocolate, very viscous, and it's not inverse or anything. So sometimes it's not even inverse. That's what I have seen. So the point of this slide is the viscosity of emulsion can be a lot more than the individual component. Okay? And the viscosity depends on how small is the droplet, right? If the droplet big, it can separate quick, right? If the droplet small, it forms a strong emulsion. How do we calculate the mixture viscosity? Mixture viscosity is a mixture of emulsion. You can estimate from viscosity of the continuous phase. Okay. Let's say we're on the left side of the graph. We have water in oil. So we have continuous phase viscosity, which is oil viscosity, multiplied by 1 minus volume fraction of the dispersed phase, or volume fraction of water. Let's say we have 30% water. So have 30% here. So 1 minus 0.3, okay, not 30. 1 minus 0.3 is 0.7. Raised to the power of minus 2.5. Last one is, I don't remember the name, but that's the name of the person who had this equation, okay? So this one showed you that the viscosity of the emulsion can be a lot more. It grows exponentially, okay? Power of minus 2.5 of that fraction. So I still have 2 minutes, okay? We can do the test. Basic sediment and water test. You centrifuge it, right? And you find, okay, the top part is water, top part is oil, bottom part is water. So method is put a certain big amount and then centrifuge it that much RPM and then centrifuge 2 to 5 minutes or something. So you get sediment on the bottom and then water layer and then crude oil and toluene. So you thin it with toluene first, right? You add toluene in to thin it. So it makes it easier to separate. Okay. All right. Let's talk about bottle test. Yeah. Bottle test, add water in, add oil in, do the mixture, stir it, and find out how quick that is separate. Okay, 1 minute, then it separate that much. 5 minutes, it separate that much. 15 minutes, separate that much. 30 minutes, separate that much. Then plot the graph. Okay, this is the percent water separate. Then you can find out how easy it is that your oil have the tendency to form emulsion. So when you do the test, you will see, oh, okay, I have tight emulsion. I have not that tight emulsion, and I should buy bigger treater for much of the tension time. Oh, it's 12:20. Okay. See you on Saturday. Okay, the bus leave at 6. We should meet at 5:45. Correct? No hard hat is needed, but we need setting glass. Thank you for coming.